In this podcast, we're going to be walking through at least the beginning part to this question. How big is the universe? How do astronomers know how big, how far away things are, how many galaxies there are, things like that. And measuring astronomical distances is the hardest thing for astronomers to do. You can't just run out a tape measure to distant stars or galaxies. They're too far apart, too far away from us. But we do have some basic skills. We can use radar, we can use stellar parallax, we can use something called a standard candle, and even there's a law named after Edwin Hubble called Hubble's law that allows us to measure really distant objects. And each one of these is kind of built on the one before. So we're going to walk through the first three in this VCAS, and we'll walk through Hubble's law in the next one. So first thing in the cosmic distance ladder is the radar. And radar, you've already should have done this lab, but it's a pretty simple lab where we use the speed of light, since it travels at a constant speed, and the time it takes for that light, in this case radar, to go to that object, bounce off of it, and return. We can actually use that travel time then and calculate the distance directly. So the sound wave, or the light wave in this case, goes from the object here on Earth, travels out, bounces off the object, comes back. This works only for the really close objects. We've done this for our moon, the planets, moons around other planets, but comets and asteroids, but that's about it. We can't go outside of our solar system for a couple reasons. A, stars don't reflect this light very well. All right, the radar light gets absorbed. Two, those objects are really, really distant. So as that light travels out, one, it's going to take forever to get there, or at least a really long time. And B, as the light spreads out, it gets dimmer, so the reflection's harder for us to see, and eventually it gets to the point where we just can't detect that reflection anymore. So the next rung up on the distance ladder is stellar parallax, and this is what we've been talking about since Unit 2. You can use this to actually determine that the sun is the center of the solar system, not the Earth. That's the apparent shifting of a star's position, all right, due to the fact that the Earth is going around the sun. All right, the more it wobbles, the closer it is. The less it wobbles back and forth, the farther away it is. Now, as far as how far out you can go, this is good somewhere around 1,000 parsecs. Now, you should have a definition of what a parsec is and a light year. Real quick, a light year is just the distance light travels in 1 year. A parsec is the distance a star is away from the Earth if it has 1 degree of parallax, 1 second of parallax, which is about 3.26 light years. But it's only good to 1,000. Now, that sounds like a lot, but it's really only a few thousand stars, maybe. All right, so if this is our Milky Way, all right, parallax right now might be something like this green circle here. All right, now we do have a new telescope in the works that may go to 10 times this amount, but still not covering the entire Milky Way galaxy, even let alone distant galaxies. There are a few things in between that that we're not going to go over using the HR diagram and main sequence fitting. But what we want to talk about next are standard candles, because these guys are kind of cool. That's how we measure distance to other galaxies. All right, standard candles are stars or other phenomenon that we know their brightness of. All right, two things that we're going to look at: Cepheid variable stars and Type 1a supernovas. What we do, if we know how bright an object is, say, for example, a light bulb, we know its brightness. And then we measure its apparent brightness. Okay, how bright does it actually appear? We can use the difference between how bright it should look and how bright it actually looks to figure out the distance, which you'll use in the Cepheid variable star lab. The reason for this is that light, as you move away from that source, gets dimmer and dimmer, but it gets dimmer and dimmer by a measurable and predictable amount. As you can see, it goes out. That light goes from 1 square, then to 4 squares, and this 9 squares. It's called an inverse square law. Basically, if I have a 100-watt light bulb here, I go out a certain distance, it looks like 100 watts. And then if I go out to double that distance, it would go down to what a 25 watt bulb would look like, because it went down by the square. And then it would go down by to say about a 10 watt light bulb ish. All right, and so on. But it's a predictable amount that we can use to actually measure how how far away something is. And a Cepheid variable star is a star that actually gets bigger and therefore more luminous, and then shrinks in size and becomes less dim, or it becomes more dim. And the interval, okay, how often it gets brighter and dimmer, actually is related to its absolute magnitude. So in other words, we can look at how often it flicks on and off its brightness, and that will tell us its absolute magnitude. The other one is this type 1 supernova. Now, a type 1a supernova is a supernova. It's a star exploding, but it's specific to the conditions. All right. So first off, we start off with a binary system. One of those being a white dwarf. All right. That white dwarf, again, you kind of remember from last unit, small hot ball of carbon. All right. Didn't have enough mass to burn anything past carbon. What happens, though, is eventually the companion star begins to turn into a red giant. And when that happens, all of those outer layers get sucked into the small white dwarf. So the white dwarf mass starts to increase and get bigger and more hot. And as it gets hotter and hotter, it will reach a point where it can overcome the forces preventing nuclear fusion of carbon. And this critical limit is at about 1.4 solar masses. So once it gets heavy enough, it has enough gravitational strength to actually run through the other nuclear reactions. It's just this runaway effect, and the whole thing explodes once it hits that point. And since we know that that mass is roughly 1.4 solar masses, and that all that energy is going to be producing the light that we see from the supernova, we can get a good idea of how bright it is. And we know that when supernovas like this are all the same. All right, here's an example of one. You can see it wasn't there, now it is that we can actually watch the light curve. It gets really bright, and then over the course of months it fades. And they all look like this, all the type 1As. So that's another standard candle. Now, how is this going to actually determine how big the solar system, or excuse me, the universe is? Edwin Hubble used the Cepheid variable stars specifically to answer, or begin to answer, this question. In the 1920s, we thought we had one galaxy, the Milky Way galaxy. It was just known as the universe at the time. All right, one galaxy. And that galaxy contained maybe 100 billion stars or more. That's a lot of stars. And other things, planets and nebula. All right, and nebula were these just puffy, wispy clouds. We've kind of talked about them before. All right. Certain ones kind of look spirally. All right, and it was these spirally galaxies that Edwin Hubble wanted to measure the distances to. All right, and he was going to use those distances, which he thought these objects were about as far out as you could go, to actually determine the age of and the size of the universe. Now, real quick, how in the world can a distance tell the age? All right, this is going to be kind of a little sidetrack here. But first off, the speed of light is really fast, but it's not instantaneous. It's 186,000 miles per second, or 300,000 kilometers per second. And really, when we see the sun rise, we actually see the sun how it was 8.5 minutes ago, because it takes 8.5 minutes for that light to travel the 93 million miles to get to us. So we actually are starting to look into the past. We see the sun as it was 8.5 minutes ago. If I look out to stars that are 4 light years away, I'm really looking to the past of that star 4.5 years. If I look across the Milky Way galaxy, which is 100,000 light years across, I am looking back in the past 100,000 years. All right, because it takes light time to actually travel. As this shows, if this star explodes right now, and it's 3,000 light years away, what the observer sees is not that it explodes immediately, but that it explodes 3,000 years after the fact. All right. So supernova occurred. We didn't see that happen until 3,000 years after because of the distance and the time it takes for light to travel. So back to this, if we determine the distance to the most distant object we can see, we know how far away that is, and obviously we know how long that light's been traveling to us, and we can get a good idea of how old it is. Before Hubble started his work, we thought maybe 100,000 light years away is the most distant object, so therefore the universe is about 100,000 years, which was a problem because they had radiocarbon dating and they knew that the Earth was much older than that. So here's Edwin Hubble. He wanted to measure the distance to these spiral nebula, all right, which were, he thought, on the edge using the Cepheid variables, as I've mentioned. And those Cepheid variable stars get brighter and dimmer, and he found them using the biggest telescopes of the day. And when he went and actually calculated the age of these things, he found that the universe is much, much bigger than anyone before ever thought. In fact, he found that these galaxies aren't in our own little universe, our own Milky Way, but they're actually their own island universes. And each one of those are millions of light years away, which means we're looking millions of years into the past, and that each one of those contains billions and billions of stars. So then the next question I'd hope you'd ask is, well, how many galaxies are there? So how big is the universe? All right, let's fast forward to 1995. The Hubble Space Telescope is launched and is going to make something called the Deep Field picture. What the Deep Field picture is, I'll show that movie later, is basically the Hubble Space Telescope stared at what they thought was just blank space, that no telescope here on Earth actually saw a star in this region. And it was going to stare at that blank spot in the sky for 10 full days. And while it's doing that, it's taking pictures and exposing so that it can see the faintest and most distant, hopefully, objects that it could find. Some people thought it was a waste of time and they wouldn't see anything. But in fact, this is what it saw. This is the Hubble Deep Field image. And there are actually about 3 stars in here. That's a star, that's a star, and that's a star. Everything else in here, that's a galaxy with billions of stars in it. That's a galaxy with billions of stars in it. Even these little guys are little galaxies with maybe billions of stars in it. Every single speck on there is a galaxy. And what should blow your mind even more is that picture is the size of a tennis ball at 100 meters. Tennis ball? And if you were to take that image and just spread it out throughout the entire sky, what we would have to get is that the universe contains anywhere from 50 to 100 billion galaxies, and each one of those containing hundreds of billions of stars. That is absolutely incredible how many galaxies and stars there are out there. So to help maybe put this in a different perspective, another young man actually made a video that I think you'll find entertaining about this size of the universe that I want you to look at. And if you're watching on YouTube, just click right here and it'll link you to it.